Hello, I'm Aiden Grossman, and this is my presentation on my project where I designed a microstepping solenoid using EMWorks EMS. So first off, we're going to go over some of the design work and how EMWorks EMS was used to guide many of the design decisions that were made. So the overall design involved 4 separate coils that could be driven independently using constant current drive circuitry. And this was done to vary the force of each coil acting on the plunger to allow for microstepping, where the plunger can be moved in small increments by varying the power in the coils around it. And this was all simulated using EMWorks EMS for overall proof of concepts and also later optimizations of designs, but we'll get into that a little bit later. So optimizing design variables was done using EMWorks EMS within Autodesk Inventor to optimize certain design variables such as plunger length, and also to provide proof of concept data that would help guide further design decisions. Most of the design variables are fairly fixed due to other constraints, but some were optimized through simulation, mainly plunger length. So as you can see right here, we have a graph of plunger length. You can see how one of the simulated versions was 10 millimeters, the other was 20 millimeters, and the other was 30 millimeters. And this was one of the big variables where I wasn't really sure how it would end up working out. So I was able to use EMWorks EMS to simulate all of the different combinations, especially over the entire length of the solenoid. And in the end, a 20 millimeter plunger was selected. A PCB was designed with a microcontroller and 4 separate constant current drivers. The microcontroller ran software that controlled the constant current drivers and allowed for microstepping and completely independent control of each constant current driver, which allowed for the microstepping to take place. So manufacturing was done using a custom-built coil winder, 1 coil at a time. 500 windings of 28 gauge wire were wound onto each coil, as you can see right here. I have the coil winder that was custom built for this project, and we'll look at that now. Here's the coil winder that was shown in the presentation. Right here is the part where the solenoid is mounted with a stepper motor right here that turns it, that pulls the wire onto the solenoid. And then you have right here with the part that contains the spool of wire and a couple pieces of mechanical components that guide the wire into the nozzle right here that further guides the wire onto the solenoid. And this is mounted on a ball screw and a linear rail, and it moves back and forth in order to control where the windings are going. And then here we have the circuit board in final assembly. The circuit board is manufactured using standard techniques. It was soldered by hand, and everything was wired together by connecting the solenoid to the PCB through some solder joints that you can see in the image there. And then the PCB there were a couple bodges that were needed, mainly the Zener diodes that you can see here that acted as flyback diodes that were emitted from the initial design. And that's it for that phase of the manufacturing. Now we can go take a look at it and see exactly how everything came together. Here you can see the circuit board along with the solenoid attached to it. Again, there are 4 constant current channels, one for each coil on the solenoid. You can see the plunger that's within the solenoid currently. That's currently a 30 millimeter ferromagnetic plunger. It's ANSI 1018 low carbon steel. And when I turn it on, you'll be able to see the plunger move through the solenoid, and then it'll move back to the other side. So you can see it moving. It's skipping around a little bit because the coils aren't exactly generating an extremely strong electromagnetic force, and also there's some internal friction within the solenoid due to the choice of manufacturing of the solenoid and also the choice of plastic. In a second here, you can see it pop right out on the other side using some fairly smooth movement. In conclusion, a 4-coil microstepping solenoid is created that was able to fully demonstrate microstepping with design decisions guided using the EMWorks EMS software. The solenoid was driven using 4 constant current channels on a circuit board, and that's all. Thank you for watching.